dessert shop in Pasadena, California. Ordered it with whipped cream, of course. When it arrived at the table, I saw no trace of the stuff. After I told the waiter that my cocoa had no whipped cream, he asserted I couldn't see it because it sank to the bottom. But whipped cream has low density and floats on all liquids that humans consume. So I offered the waiter two possible explanations. Either somebody forgot to add the whipped cream to my hot cocoa, or the universal laws of physics were different in his restaurant. Unconvinced, he defiantly brought over a dollop of whipped cream to demonstrate his claim. After bobbing once or twice, the whipped cream rose to the top, safely afloat. What better proof do you need of the universality of physical law? Chapter 3. Let there be light. After the Big Bang, the main agenda of the cosmos was expansion, ever diluting the concentration of energy that filled space. With each passing moment, the universe got a little bit bigger, a little bit cooler, and a little bit dimmer. Meanwhile, matter and energy co-inhabited a kind of opaque soup in which free-range electrons continually scattered photons every which way. For 380,000 years, things carried on that way. In this early epoch, photons didn't travel far before encountering an electron. Back then, if your mission had been to see across the universe, you couldn't. Any photon you detected had careened off an electron right in front of your nose, nano and picoseconds earlier, a billionth and a trillionth of a second. Since that's the largest distance that information can travel before reaching your eyes, the entire universe was simply a glowing, opaque fog in every direction you looked. The sun and all other stars behaved this way too. As the temperature drops, particles move more and more slowly, and so right about then, when the temperature of the universe first dipped below a red-hot 3,000 degrees Kelvin, electrons slowed down just enough to be captured by passing protons, thus bringing full-fledged atoms into the world. This allowed previously harassed photons to be set free and travel on uninterrupted paths across the universe. This cosmic background is the incarnation of the leftover light from a dazzling, sizzling early universe, and can be assigned a temperature based on what part of the spectrum the dominant photons represent. As the cosmos continued to cool, the photons that had been born in the visible part of the spectrum lost energy to the expanding universe, and eventually slid down the spectrum, morphing into infrared photons. Although the visible light photons had become weaker and weaker, they never stopped being photons. What's next on the spectrum? Today, the universe has expanded by a factor of 1,000 from the time photons were set free. And so, the cosmic background has, in turn, cooled by a factor of 1,000. All the visible light photons from that epoch have become 1/1000th as energetic. They're now microwaves, which is where we derive the modern moniker cosmic microwave background, or CMB for short. Keep this up, and 50 billion years from now, astrophysicists will be writing about the cosmic radio wave background. When something glows from being heated, it emits light in all parts of the spectrum, but will always peak somewhere. For household lamps that still use glowing metal filaments, the bulbs all peak in the infrared, which is the single greatest contributor to their inefficiency as a source of visible light. Our senses detect infrared only in the form of warmth on our skin. The LED revolution in advanced lighting technology creates pure visible light without wasting wattage on invisible parts of the spectrum. That's how you can get crazy-sounding sentences on packaging, like 7 watts LED replaces 60 watts incandescent. Being the remnant of something that was once brilliantly aglow, the CMB has the profile we expect of a radiant but cooling object. It peaks in one part of the spectrum, but radiates in other parts of the spectrum as well. In this case, besides peaking in microwaves, the CMB also gives off some radio waves and a vanishingly small number of photons of higher energy. In the mid-20th century, the subfield of cosmology, not to be confused with cosmetology, didn't have much data, and where data are sparse, competing ideas abound that are clever and wishful. The existence of the CMB was predicted by the Russian-born American physicist George Gamow and colleagues during the 1940s. The foundation of these ideas came from the 1927 work of the Belgian physicist and priest Georges Lemaitre, who was generally recognized as the father of Big Bang cosmology. But it was American physicists Ralph Alpher and Robert Herman who, in 1948, first estimated what the temperature of the cosmic background ought to be. They based their calculations on three pillars. 1. Einstein's 1916 general theory of relativity. 2. Edwin Hubble's 1929 discovery that the universe is expanding. And 3. Atomic physics developed in laboratories before and during the Manhattan Project that built the atomic bombs of World War II. Herman and Alford calculated and proposed a temperature of 5 degrees Kelvin for the universe. Well, that's just plain wrong. The precisely measured temperature of these microwaves is 2.725 degrees, sometimes written as simply 2.7 degrees. And if you're numerically lazy, nobody will fault you for rounding the temperature of the universe to 3 degrees. Let's pause for a moment. Herman and Alford used atomic physics, freshly gleaned in a lab, and applied it to hypothesized conditions in the early universe. From this, they extrapolated billions of years forward, calculating what temperature the universe should be today. That their prediction even remotely approximated the right answer is a stunning triumph of human insight. They could have been off by a factor of 10 or 100, or they could have predicted something that isn't even there. Commenting on this feat, the American astrophysicist J. Richard Gott noted, predicting that the background existed and then getting its temperature correct to within a factor of 2 was like predicting that a flying saucer 50 feet wide would land on the White House lawn, but instead, a flying saucer 27 feet wide actually showed up. The first direct observation of the cosmic microwave background was made inadvertently in 1964 by American physicists Arno Penzias and Robert Wilson of Bell Telephone Laboratories, the research branch of AT&T. In the 1960s, everyone knew about microwaves, but almost no one had the technology to detect them. Bell Labs, a pioneer in the communications industry, developed a beefy horn-shaped antenna for just that purpose. But first, if you're going to send or receive a signal, you don't want too many sources contaminating it. Penzias and Wilson sought to measure background microwave interference to their receiver to enable clean, noise-free communication within this band of the spectrum. They were not cosmologists. They were techno-wizards honing a microwave receiver and unaware of the Gamow, Herman, and Alford predictions. What Penzias and Wilson were decidedly not looking for was the cosmic microwave background. They were just trying to open a new channel of communication for AT&T. Penzias and Wilson ran their experiment and subtracted from their data all the known terrestrial and cosmic sources of interference they could identify. But one part of the signal didn't go away, and they just couldn't figure out how to eliminate it. Finally, they looked inside the dish and saw pigeons nesting there. They were worried that a white dielectric substance, pigeon poop, might be responsible for the signal, because they detected it no matter what direction the detector pointed. After cleaning out the dielectric substance, the interference dropped a little bit, but a leftover signal remained. The paper they published in 1965 was all about this unaccountable excess antenna temperature. Meanwhile, a team of physicists at Princeton, led by Robert Dicke, was building a detector specifically to find the CMB. But they didn't have the resources of Bell Labs, so their work went a little slower. And the moment Dicke and his colleagues heard about Penzias and Wilson's work, the Princeton team knew exactly what the observed excess antenna temperature was. Everything fit.